In this video, we're just going to show how you can graph the terms of a sequence very quickly, and also you can do this on a graphing calculator, which I can't cover in this video because I don't have a TI online. But essentially, we're just going to do this by hand. So we say, graph the first 6 terms of each sequence, then use your graphing calculator to verify your results. The idea is this: we want to graph the outputs for this given rule, okay, or this sequence of numbers that happens in order. So what we're going to do is, if we're going to graph the first 6 terms of this, we need the first 6 terms of this sequence, okay? So we say A1, A2, A3, and so on and so forth. We want all of these things. So now we can write them out in what we call roster notation, or we could even make a T-chart of values. So we say the term and then the output of that term. So we say 1, 2, 3, 4, 5, and 6. And I'm actually really partial to this tabular format here. So we say, all right, well, 2n minus 3, if that's our rule, then basically it's saying, well, whatever term you are, like if you're the first term here, to get the output, you take 2 times the term number, so 2 times 1. So we get 2 times 1 minus 3. In other words, we get 2 minus 3, we get negative 1. Okay. Going a little bit more quickly here, we say negative 1 is the first term in our sequence here. If we were to plug in 2, we get 2 times 2 minus 3, which is 4 minus 3, which is 1. Then we say, 2 times 3 minus 3 is 6 minus 3 is 3. We can see that our pattern here is going up by 2 every time, okay? And the only reason I mention this is because if we were talking about functional math, y equals mx plus b, this would be y equals 2x minus 3. This is just a line, okay? So essentially, we know that this sequence goes on, indefinitely, but we want to graph the first 6 terms. We say, really what we want to indicate here on the x and y axes is that our x-axis is our term. This is the term number here. And we say that the y-axis here, this is our term output. So I'm going to write term output, and I'm also going to write, in this case, a sub n, where this is our n, okay? So you'll notice that when you graph sequences, you're always going to be starting, say, up in, the right side of the y-axis, because you're always starting with your positive 1 for your term value. So we say positive 1 mapped onto an output of negative 1. So we say that this right here shows that our first term was at an output of negative 1. That's all it's showing, okay? And then our second term here, we got 2, 1. So we're going to graph this just like we would graph a function, 2, 1. We have over 3, up 3, so over 3, up 3. And you'll notice that we do get this linear looking graph here, but basically this is showing that these are the terms of your sequence, and these were their output values right here. So you notice we got negative 1, 1, 3, 5, and 7 for the first 6 terms, our first term, second term, third term, fourth term, and fifth term. And I guess the 6th term I didn't even graph. We say 6 comma 9. But this is the terms of our sequence here. So now let's take a look at b sub n. Again, I'm going to recommend every time that we put in a table of values here. So we say term number, and I wanted the first 6 terms. So we say go ahead and put these into our table here. We say b sub n. Now in this case we get something a little bit different. We get 2 plus, in the first case we get 6 over n. And in the first case we have n is 1. So we say 2 plus 6 over 1 is 8. Okay, so we're going to take that out of there. We say we get 8. And if I were to plug in a 2 now, we say 6 over 2 is 3. So 2 plus 3 is 5. So I get 8, 5. We say now let's plug in a 3. 6 over 3 is 2. So 2 plus 2 is 4. So I get 4. And then if we plug in a 4 here, we say 6 over 4 is 3 halves or 1.5. And 2 plus 1.5 is 3.5. So we get 3.5. If we were to plug in a 5 now, this is 2 plus 1.2, so 3.2. So we get 3.2, and you can see that this is kind of narrowing in on a value here. We say one more here. If we were plugging in a 6, we get 2 plus 1, which is 3. So graphing out the terms of this sequence, we say our first term is 1, 2, 3, 4, 5, 6, 7, 8. It has an output of 8 here. Our second term had an output of 5, so 3 less than this. Our third term had an output of 4, so 1 less than that. And then our fourth term was at 3.5. And then our next term, fifth term, was at 3.2, so a little bit lower. And then our sixth term was exactly at 3. So now, let's talk about this. I do want to kind of mention this here. Should we connect the dots? And what I want to tell you is don't connect the dots. So we say don't connect the dots. And the reason why is because if you connect the dots, then what you're saying is that we covered every single term value, which we would get this asymptotic thing here. Every single term value existed. That is, I could have, like this was between our 5th term and 6th term, you could have an A 5.5th term in your sequence, which we know is absurd to say. Your sequence can only have like a first term through like whatever term, but can't have a 5.5th term. So this sequence can keep being graphed here, but we only graph this finite sequence. We stopped at n is 6, but that's how you graph them.